For fluid mechanics presentation, we gather information to explain what controls fluid circulations in the oceans. There are two main ocean currents, surface currents and deep ocean current. Surface currents depends on many factors include wind, the Coriolis effect, and the tides in the ocean. This makes finding accurate calculations difficult. Alternatively, deep ocean currents lie beneath the surface currents and are not impacted by wind. We began to examine both surface and deep ocean currents in our presentation.
So for our hypothesis, we found that in addition to considerable geological factors, including wind, gravitational pull, and the Earth's rotation, there are other variables that influence the fluid circulation in the ocean. We believe that pressure and density can be important controlling factors in current velocity as well. In deep ocean currents, density is the main drive for this process. Water with a higher salinity will have a higher density as well as current velocity and can be changed in different density areas. For the surface current, different atmospheric pressure in different temperature areas can drive currents by changing its velocity.
From this video of the Earth's major ocean currents, we can see that the red warmer currents are traveling noticeably faster than the blue colder currents. These warmer currents travel faster because they have a higher temperature. Warmer currents tend to travel faster because they have a less atmospheric pressure due to the existing climate. Deep ocean currents are formed from dense water near the poles of the Earth. Cold polar air cools the water and lowers its temperature, increasing its salinity, thus increasing its density. Fresh water freezes out of seawater to become sea ice, which also increases the salinity of the remaining water. This very cold, very saline water is very dense and sinks. This sinking is called downwelling. These dense currents travel much slower than the warmer surface currents. We prove this by deriving the following equation.
Well, from the equation, we built two models for the surface current and the deep ocean current. Well, for the first one is for the surface current, we set up the cold and hot area with different atmospheric pressure, and we assume the height and density are equal in that situation. After we derived from the Bernoulli equation, we found out that the less the atmospheric pressure, the greater the velocity. And also, since the Earth has like two different main temperature range, like cold and hot, so this analysis for the assumption is worked out for the surface current. And for the deep ocean current, I built a model for different density. Rho 2 is greater than Rho 1 at here, and also the heights and the pressure are assumed to be equal. So after deriving the equation, we found out that as the density increase, the velocity will increase. So it's just like when during the process, the currents is split up by this kind of relationship. So it causes the circulation of the current.
So after completing our group project together, we can conclude that since temperature affects pressure, we know that the surface currents in a warmer climate with less atmospheric pressure have greater velocity than the surface currents in cold area. And we came to this conclusion from the Bernoulli equation. Furthermore, we used Bernoulli's equation again to conclude that salinity affects currents. The saltier a current is, the more dense it becomes, and it makes it travel at a higher velocity than a less dense current. Thank you.